Alrighty, let's take some derivatives for our warm-up. So this is the warm-up. We have 4 to do, so let's give them a try. Alright, so for the first one, we took the derivative, and the derivative form is this. And I simply plugged in my 5x squared into wherever it's cx. So I saw plugged in here, I plugged in here. But because we have to deal with chain rule, we also have to multiply by the derivative of 5x squared, which is 10x. So for the second one, I first wrote down what the derivative would look like if it was just x. Then I just plugged in 4x to the fourth, because that's what we have here. And I multiplied by the derivative of that for the chain rule. For the last two, you follow the same principle. Just find out what the derivative of a cotangent would be, and then put the 2x to the fourth, and then multiply whatever you get by the derivative of 2x to the fourth. And then do the exact same thing for number 4. Alrighty, let's do the next problem. That's an asteroid problem. A star-shaped curve in figure 4.7h is called an asteroid. Its parametric function is given right here. Find the equation for dy dx. Alright, that's not going to be bad at all. And then evaluate the point xy when t equals 1 and find dy dx when t equals 1. Write the equation of the line tangent to the point, blah, blah, blah. Okay, so that's not bad at all. So let's do this problem. So the first thing we want to do is find the derivative of the dy dx dt and dy dt. So they're right here. This is your dy dt. This is your dx dt. So to find dy dx, you just divide the two. So over here is how I divide them to 2. And if you multiply top and bottom by dt, you can see that they would cancel out, leaving you with this. And if you were to divide them, some cancellations are going to happen. The cosine here would cancel out 1, the cosine's right there. Sine would cancel out 1, the sine's right there, leaving you with negative tangent. Now, if you want to know what the derivative would be at t equals 1, you can simply plug in t equals 1. But what we did right here instead, we have our x and y's when t equals 1. So your x1 would be this, and your y1, okay, the x1 would be right here, and your y1 would be right here. And then to find dy dx at t equals 1, you plug in 1 into that derivative we've recently found, which is right here. And now we have everything we need in order to create a line. Because here's your y1, which is right here. This is your x1, which is right here. And then here's your slope, which is right here. So you plug these 3 things in, and you get your final equation right here. Did they even ask for the final equation? Right, an equation, yeah, they did. So once you find out what your point is at t1, you have to find out what the slope is at t equals 1, and then you write the equation. Alrighty, so not too bad. That was a fairly easy problem. Alright, here's the second problem. Eliminate the parameter t. To do this, transform and solve the 2 equations for the squares of cosine of t, the squares of cosine t and sine t in terms of x and y, then use the Pythagorean property for sine and cosine. Alright, but if you are familiar with this one, is sine squared plus cosine squared equals 1. Let's go ahead and do this problem. So let's look at the first one. So if you first had x equals 8 cosine cubed of t, so to get cosine by itself, you first divide by 8 on both sides, and then take the cube root. Now you have your first piece of the puzzle, which was rewritten right here. Then you do the same thing for the sine. You first divide both sides by 8, which you should have gotten 1/8 y. Then you take a cube root, and then 8 becomes a 2. Cube root of 8 is 2. And now we have a sine. Now you know what sine and cosine is. Now you can write the equation. Sine squared plus cosine squared equals 1. That's just an identity that you should know. So, into sine, plug in whatever sine represented. Into cosine, do the cosine one. Square the 2. So the cube root means to the 1/3 power, by the way. Square the 2, and you should end up with this. So your equation, when you make it look more simple, is right here. Now our equation is already in terms of y's and x's, but if you want to solve it for y, you can do that as well, and you should end up with this value right here. So let's do another one. Given these two parametric functions, go ahead and find the equation for dy dx in terms of t, and then calculate that when t equals that. Okay, that's the exact same thing as the first example, so let's do that real fast. Alrighty, so I did the x one first. We, after doing some chain rule stuff, you should have ended up with this expression right here. So let's do this one now. Alrighty, now having done dy dt, oops, that's not my highlighter. You should have ended up with 5 pi cosine of pi t. If I made a mistake, just tell me tomorrow in class. So now that I have dy dt dx dt, you can simply find this by dividing one over the other. So dy dx is dy dt over dx dt, and when you divide the two, you're going to end up with this one right here. Now, unfortunately, you cannot combine the cosine and the sine in this case to make it a cotangent. That's because the insides are not the same. You would actually have to use the identity, because there is actually an identity you can use when sine is has a degree twice as big as the cosine, but I'm not going to go into that right now. So that will be the answer. To calculate what it would be if t equals 0.15, you simply plug in 0.125 into t and see what you get. Alright, I'm going to stop the video right here. I see you guys tomorrow.